Okay, good morning. Welcome to
FamilyMath486a.
FamilyMath486a. So, yesterday we talked about why the real numbers were bigger than, had a bigger infinity than the counting numbers.
Yeah.
And this is what Kelsey Houston Edwards' video was about. And how did this argument work?
So we made a list of the real numbers.
Okay. Here's real number 1, 2, 3, 4. Okay, and I'll just write some out.
And then we applied 2 rules to these numbers. We're going to make a new number, and we're going to use the two rules to make one. And the first rule, I think from our movie yesterday, was if a number is not 8, make it 8. And if the second one is if the number is 8, make it 4.
Okay. So with our, okay, so we're going to look at some digits, and if it was 8, make it not 8, or make it 4, and if it wasn't 8, make it 8. And what digits are we looking at?
We're going to look at the first digit of the first number, second digit of the second number, third of the third, fourth of the fourth, ...
Okay. So I'll change the rule a bit because we got 2 zeros here. So if it's 0, I'll use 8 again, and not 0, make it 0. So we're going to make a new number, which is 0.08
0, 8, 0,
8, and then however it continues on.
Yeah.
And can you explain to me why this number cannot be on our original list?
So if you look at the first digit of our number and the first digit of the first number,
Yep.
they don't match, so it doesn't equal this one.
Okay. So the first digit of our number is different than the first digit of the first number. So it can't be the first number.
And then the second digit of our number and the second digit of the second number don't match, so
Okay.
the second number can't be our number.
All right, good.
The third digit of the third number and the third digit of our number aren't the same, so it can't be.
Okay, and
And then the fourth digit of the fourth number, and it just keeps going.
all the way down. So it's different. So no matter how we list the numbers out, we can always make a new real number that's different.
Yeah.
So that means we can never list them out completely.
Yeah.
And that's the argument why the infinity of real numbers is bigger than the infinity of counting numbers. So last night when we were chatting, I said there's a surprising fact that the rational numbers a over b, so let's say positive, so a and b, a greater than 0, b greater than 0 integers. Okay. So numbers like 3/2 or 9/4 or 1081 over 37. These numbers, unlike the integers, when you put them on the number line, so here's 0, 1, 2, 3. These numbers seem to fill everything up.
Yeah.
Right?
But I don't think they do fill everything up.
Well, sure. We certainly miss numbers like
Pi,
we've talked about is not a
square root of 2.
Yeah, but they're pretty dense. Actually, that's the word in math.
Yeah.
And so you might think that the rational numbers have the same infinity as the real numbers, but the surprising thing is there's the same number of rational numbers as there are integers. And this seems implausible, right?
Yeah.
You asked me a question last night about this, but the whole reason we're doing the project. Do you remember what the question was about the rational numbers and how dense they are and everything?
No.
No? You asked me why the same diagonal argument doesn't work that we just did for the real numbers.
So,
Why don't we do the same thing? Write down the rational numbers and make a new rational number.
because,
Do you remember asking that question?
yeah.
Okay. All right. So let's talk about that.
Okay.
Okay?